Welcome back to the Deep Dive. We are the shortcut to being well-informed, taking your stack of source material articles, research, specialized notes, and distilling the crucial insights you need right now.
Today, we are strapping in for a deep dive into the very fabric of data organization in C++ up. We're looking at two related but essential structures.
Yeah.
The pair and the tuple.
Yeah, and these are, they seem simple on the
It's
surface.
deceptively simple, but they're absolutely foundational.
Our mission today isn't just to, define them. We need to understand the relationship between these two, what tactical advantage each one offers, and most importantly, how they go from being these theoretical library components to being necessary setup tools in high-pressure situations.
Like competitive programming.
Yeah.
That's exactly right. The source materials you provided are fantastic because they don't just give us the technical specs, the headers, the definitions.
Right.
They give us concrete examples, like specific problem hints from platforms like Kattis that really show the critical application of these things.
So we're connecting the syntax to the strategy.
That's the goal.
Okay, let's unpack this, starting with the original, the foundational building block, the pair. What exactly defines this little workhorse?
The pair is really where simple data grouping begins. It's a container designed to group exactly two related values into a single entity.
Just two.
Just two. And the key feature here, which I think a lot of people overlook when they're first learning, is that these two values can be of completely different types.
Heterogeneous.
Exactly. Heterogeneous. Think of it like creating a custom key value association on the fly. You might be pairing, say, a string with the double.
And we see in the sources that this structure lives in the utility header, which that kind of speaks to its fundamental nature, doesn't it?
It really does. It's formally defined as a class template.
Yeah.
std.pair t1, t2.
Meaning you, the programmer, decide what T1 and T2 are when you use it.
Correct. It could be an object and an integer, two different structs.
Yeah.
Anything. The pair's only job is to make sure those two elements are always treated as one unit.
Now, here's where a curious programmer might challenge us. If I need two related items, why wouldn't I just define a tiny custom struct, with two named fields? Why rely on the generic pair?
That's a brilliant question, and it speaks to the trade-off. If you're building a large system, a well-named struct is always better. Always. For readability. But in scenarios like competitive programming or just quick utility functions, defining a new struct for every two-item group is.
Yeah.
It's just tedious. A pair offers extreme convenience.
Zero boilerplate.
Zero declaration
No.
boilerplate. You just use it
Right.
instantly. Plus, because it's a standard library thing, it comes with features built in, like comparison operators that make it immediately usable inside other containers.
Like std.vector or std.map.
Exactly.
So it's the ultimate tool for that quick throwaway data grouping where boilerplate is a total time killer. And accessing the elements is super easy. You just use the named members, first and second.
Right. If you have a pair tracking a coordinate, you just know first is X and second is Y.
Yeah.
What's fascinating here is the conceptual relationship this simple structure has with the generalist container we're about to discuss, the tuple.
Ah, okay.
While the pair is incredibly useful on its own,
Yeah.
our sources confirm that technically, a pair is just a special case of a tuple.
Simplest possible version.
The simplest possible version. It's a tuple that is constrained to exactly two elements. It's like the two-seater convertible in the tuple family.
That structural insight helps us transition perfectly. So we get the pair, its brilliance is its rigidity, it solves the two-element problem perfectly. But what happens when our problem demands 3 or 4 or even 10 related values?
That's where the generalist steps in.
The tuple.
Absolutely. If the pair is built for just two, the tuple is there for, well, everything else.
Yeah.
It is the generalized solution for organizing a fixed but potentially large number of elements,
And they can still be of different types.
all of which can still be of different types. It essentially solves the problem of needing a temporary custom struct without needing to actually declare one.
So if I needed to track a user's session data, let's say their user ID, which is an int, their score, a double last page visited, a string, and are they logged in, a Boolean. That's 4 different types of data.
Right.
The pair is instantly out.
Instantly out, and the tuple is in. And the technical definition really reflects that flexibility. The tuple lives in its own tuple header. And instead of just T1 and T2, it's defined as std.tuple types.
Okay, that type's notation. It sounds like serious computer science jargon. Can you break down what a variadic list of types really means for the listener?
It's just a fancy name for the ability to pass in a variable or varying number of types. It lets the container generalize.
So you're not locked in.
Not at all.
Yeah.
You can create a tuple with 2 types, 3 types, 20 types,
Yeah.
all defined right there in that list.
Yeah.
It's the mechanism that breaks the rigid 2-element constraint of the pair. That
Yeah.
flexibility is its superpower.
That makes sense. But if I have a tuple with 10 elements, I can't use first or second anymore. So how do I actually get to those elements? That seems like a really crucial point.
It is. It's the single biggest operational difference.
Mm-hmm.
Because tuple elements don't have built-in names, you access them using std.getTn.
Okay, so n is the index.
It is, and it's zero-based. So the third element is std.getTo of your tuple.
That's straightforward, but maybe less readable than first and second.
It can be, for sure. But for modern C++ programmers, there's a hugely powerful nugget you need to know. Structured bindings.
Ah, C++17.
Yes. If your compiler supports C++17 or later, you can unpack a tuple, or a pair, for that matter, immediately into named variables. You can just write auto, then in brackets, aid, score, last page, log it in, my tuple.
Oh, that is fantastic. That completely bridges the gap, doesn't it? Between the convenience of the pair and the flexibility of the tuple, you get readable names back.
It's a game changer. It absolutely is.
Here's where it gets really interesting. Theory is great, but these tools are built for solving problems. So why would a programmer, in the middle of a timed coding challenge where every line counts, choose one of these?
Right. What's a practical application?
We need to look at how they're used to enable complex algorithms.
We can start with the testing LEDs problem. It's referenced right in the source material. Imagine the scenario. You're tracking a series of events where LEDs turn on or off, and you need to find the light that turned off earliest.
Okay, so the input data gives you a timestamp and a state, on or off.
A time and a state, yeah. 2 separate data points. And the hint points directly toward the solution. Use a vector of pair.
So group them together.
Exactly. But the strategic insight here is not just that you can group 2 variables. The insight is that grouping them immediately enables the necessary next step.
Sorting.
Sorting.
But what's wrong with just using 2 parallel vectors? You know, one for the time, one for the state.
That's the classic data management headache. If you have 2 separate vectors, times and states, and you sort the times vector,
You've lost the connection.
you've completely destroyed the correspondence with the states vector. You've lost track of which state belongs to which time. You'd have to write all this complex, inefficient code just to manage the indices.
And it's slow and full of bugs, probably.
Well, for sure. But by using a vector pair time type, state type, every single entry is a cohesive record. Time, state.
They're glued together.
They're glued together. So when you sort the vector, C++ standard sort knows to keep the time and state together. The pair acts as the necessary glue that enables that crucial sorting step. It transforms the problem.
That's a perfect illustration of structure-enabling strategy. The structure isn't the final answer, but it makes that efficient n log n sorting solution possible.
Exactly.
And we see a very similar mechanism in the second source example, the club pizza problem.
Yeah, the club pizza problem requires a greedy algorithm. That's an optimization technique where you make the best local choice, hoping to find the global best outcome.
And to make that best local choice, you need your data ordered optimally.
Right. And once again, the suggested implementation relies on a vector of pair.
So what are we grouping this time?
This time we're grouping the data for the decision. You're pairing the club time with the number of pizza slices an individual can eat.
The value you want to maximize.
The value. You need to know both pieces of information at the same time to make the optimal greedy decision.
And the moment you have that time slices pair, the source material explicitly says to sort the vector.
Exactly. So we have 2 totally different challenges. One for event tracking, one for optimization, but both converge on the exact same foundational idea.
Group 2 related heterogeneous pieces of data using a pair so the whole collection can be sorted.
Yes. The pair simplifies the data model dramatically. It lets the programmer focus purely on the algorithm.
So if we connect this to the bigger picture, it's clear that these containers, they aren't just academic concepts.
Not at all.
They are critical intermediate structures. They let you transform raw, unconnected input into these meaningful bundled records that your program can then process with powerful tools like std.sort.
They save the programmer from reinventing the wheel. And under a deadline, that is invaluable.
Okay, let's synthesize this for the listener one last time. The core distinctions. Both pair and tuple are excellent at grouping related values of different types. That's the shared purpose.
Right. The defining difference is the element count
Yeah.
and how you access them. A pair is strictly 2 elements. It lives in utility, and you get that nice named access with first and second.
And the tuple.
The tuple is generalized for n elements, lives in tuple, and relies on index-based access with std.getTn, or preferably.
In modern C++s, structured bindings, to give them names.
To give them names.
So what does this all mean? It means the choice between them is it's a strategic one. It's rooted in simplicity versus flexibility.
Absolutely.
Yeah.
If you only need 2, the pair is clear. It signals your intent. If you need 3 or more, the tuple is your only standard option for this kind of grouping. It gives you the versatility for more complex data.
It's the difference between a custom-fitted glove and a versatile Swiss Army knife.
That's a great way to put it. And choosing the right one is often the critical first step to a clean, efficient algorithm.
That brings us to the end of this deep dive into foundational C++ structures. The simple containers often hold the greatest power when solving complex problems.
And before we let you go, let's leave you with one final thought to mull over, based on what we just reviewed.
Okay.
The source material showed us how the simplicity, the 2-element constraint of a pair, streamlines sorting in those examples. But what advantages might the generalized n-element structure of a tuple offer when you're solving problems that require grouping more than 2 related variables, say 5 pieces of data, before you apply a complex algorithm?
Right. Think about what kind of complex state tracking may be in pathfinding or dynamic programming becomes instantly possible when you can neatly package 5 or 6 relevant metrics into one single sortable, trackable object. That's the strategic power of the generalized container. We'll catch you next time on The Deep Dive.